Okay, today we're going just recap what we have been covered in our previous lecture. Okay, let me know if not able to hear me or not seeing my PowerPoint slide on your screen. Okay. Previously we introduced you this vector triangular for moving non-deforming control volume. So our control volume is moving. So we need this vector triangular to help us to calculate. So we introduce you the V, VCV, and W. So what is important for moving control volume is your W, which is the relative velocity W. Okay. So you need this triangular to help you to solve. And then also by looking at this triangular, vector triangular, you know that V is your resultant. So resultant is a combination of this one plus this one. The end of this arrow continue with this VCV arrow. So you want to find the resultant, you start from a starting point pointing towards the ending point. So you can find the resultant V equal to W plus VCV. Okay, this is the equation that we covered in our previous lecture. And also, we also introduced you the conservation of mass equation. But through the Reynolds transport theorem, we have modified a little bit the equation by changing the V in the control surfaces component. The capital V we change to W because we are looking at a relative velocity rather than the velocity. So because we're having a moving control volume. So this is what we cover. And we also look through a few example, right? So today we're going to look at something new, which is called deforming control volume. So we are already cover fixed control volume. We already cover fixed non-deforming, moving non-deforming. Today we look at the third scenario, which is deforming control volume. It means the control volume is changing. Okay, control volume is changing. So our Reynolds theorem, Reynolds transport theorem, which is your conservation of mass equation, which is we keep repeating so many times throughout this module. You will see this one, the first equation you see on the screen here is a moving control volume that I mentioned just now. So conservation of mass is about m dot, mass flow rate throughout the system, m dot, or mass divided by time, equal to what happened in your control volume plus your control surfaces. So if your control volume is moving, we are no longer using the V, but we're using W for your relative velocity. And if you are applying the continuity equation, then control volume plus control surfaces will be equal to 0. Okay, so you have to be sure what you're writing in the answer. So here to here is the conservation of mass equation. Okay. However, if you write your equation, you write from here to here equals 0, it will become continuity equation. Okay, make sure you understand what you're writing on your answer sheet. So if the question asks you to derive conservation of mass, you need to show the red color zone that I highlight on the screen here. You need to write from dm over dt equal to integration of cv plus integration of cs. And if you accidentally write equals 0 for conservation of mass, then I give you a wrong answer because you don't understand what is conservation of mass and continuity equation. Okay, so just be sensitive to the instruction in the question. So again, if the question asks you to derive or solve the question using conservation of mass, the expectation is the one that I highlight with the red color line from dm over dt until here. Okay, so if the question gives you instruction to solve with assume continuity equation is applied to the scenario, then we are expecting the blue color equation with 0. Okay, so don't confuse between the conservation of mass equation and continuity equation. So, okay, so these are all the free marks area that you can score marks. But also is if you careless, then you lose mark for this area. So just be careful on the control volume component. So control volume, you need to be read carefully in the statement, in the question. If it says that you have a steady flow, then this one is 0. But if the question doesn't mention anything about the flow, then there is some value for this component. You don't simply cancel and then write steady if the question doesn't mention any steady flow inside the system. Okay. So this is just some highlight of what we cover for moving control volume. Okay, this equation is for moving control volume, but today we're going to look at deforming control volume. So this is another equation that we derive from a triangular V equal to W plus CV. Okay, so you have to be sure on the triangular. So in this case, I just highlight on the screen here. You can see that the CV equal to W2 plus the control surface's velocity. Okay, CV equal to W2 plus the CS. What is W2? W2 normally refer to outlet. Okay, to outlet. Okay. So this is just some highlight notes for what is happening on the screen here. Okay. All right, let's look at the okay. Now this PowerPoint slides is basically it mentioned that when you have deforming control volume, the control volume component you have to calculate it. You cannot assume 0 anymore if you have a deforming control volume. Okay, meaning your control volume that you draw in your answer, this is the control volume that you have, is going to shrink in size, maybe become smaller. Okay, when you have a deforming control volume, then the control volume component, this whole thing, cannot be 0. There's a value for that. Okay, let's look at one example, how the deforming equation can be used. This question is available in your tutorial, chapter 2, question number 15, 1-5. So given a string that you have seen, that you see on your slides, so it's used to inoculate a cow, but in this case, what is important is what's happening inside the string here. So given that the sponger have a face area of 500 mm square, which is here. So you given the area, be careful on the unit given. It is in mm square. Be careful on the unit. All right. And the unit, the liquid in the string is to be injected steadily at the rate of this one. So by looking at the unit itself, you have a cm cube over meters over minute. Cm cube over minute. So what is this thing called? You have a cm cube over minute. Okay, let me check the attendance. Raj, you just log in, is it? Raj, are you there?
Yes, sir.
Okay, Raj, look at the screen here. I'm asking if you're seeing the cm cube over minute, what is the parameter that we are looking at? What is this parameter we call? This velocity?
It's
Or volume? Or what is that?
so I think volume because
Huh?
of the
What is this cm cube over minute? Volume, what is the unit? What is the, we know that, okay. You know mass flow rate, right?
yes, sir.
EMDT, the mass flow rate, m dot. M dot is having kilogram over second. This is mass flow rate. I'm asking if you look at the unit. Mass flow rate. So you're having a cm cube over minute. What is this parameter we call?
Volume, sir.
What is the unit for volume? You tell me. What is the unit for volume? What is the unit? Raj.
Meter cubic, sir, or centimeter cubic.
Okay, meter cubic. Is this meter cubic only? You have a over minute. What does it call?
Oh, so because of the minute, I don't know, sir. Because of the minute, maybe it's the velocity, sir.
Okay, I'll give you hints on the screen here already on the right hand side. You have a mass is following. You have a mass. Mass you know is in the unit of kilogram, and the mass is flowing. So you name the m dot in a unit of kilogram per second. You name it as mass flow rate, right? This one logic to you on the right hand side on the screen.
Oh, so sir, is
Ah,
that volume flow rate?
yes. Okay, volume flow rate. What is the normal alphabet that we represent volume flow rate?
Q, sir.
Yes, correct. Now you can recall already, Raj.
Yes, sir.
Okay. So we are given a Q here. However, the unit is in cm cube. The area is in mm. So you need to be careful on the unit when you do your calculation. Okay. Okay. Now the leakage, that we have a leakage here. The leakage rate past the plunger is 0.1 times of the volume flow rate out of the needle. So you can develop equation for this sentence. There's a leak rate there, and you're having a Q here. You have an area here. So the question asks you, find what is the speed should the plunger to be advanced. So it means that you need to push this plunger so that you have a steady flow rate Q of this one, so that the chemical that flow out from this string here can be flow with a Q, steady Q 300 cm cube over minute, because you need to consider there's a leakage rate where some flow can escape from the wall here, pass through where it will slow down the Q here. So you need to consider, and then what is the speed that you need to push? Okay, need to push, and is either the unit that the answer asking for the speed here is in cm per second. Okay, you have to before you solve, you have to know the unit that you're looking for, because you're pushing. You know that normal is meter per second. However, if you apply meter to a string, it's not logic. It's like you telling a nurse to push the needle in a meter per second. The nurse or the medical staff cannot understand how to measure meter on the string itself, because string here is measured in cm. So be careful when you tell or apply what is in your calculation. Then you need to convert the information to the medical staff or to the end user. Okay, so just be careful on the unit here. Okay, let's start. How do we solve? First, you need to sketch the free body diagram, or the diagram for the system itself. So most of the time, the diagram won't be given, right? For this module, most of the time I'll give you a scenario. You need to sketch the 2D diagram or the free body diagram for the scenario. For this example, you need to roughly know how the string work. So you have a pusher here, and then you have a body of the string, and then you have a head of the string, and so on. So the first step, you draft the solid line, which is your vessel or your system. Second, you draw the control volume. Second step, control volume means you draw the red color region that you are interested to solve. Okay, now why we need control volume again? Through control volume, it gives us two information. It gives you where is your input, where is your output. These are the important area, or the reason why we need to define our control volume. It will tell you where the flow going in, where the flow going out. Okay, and what happened to your control volume or control surfaces in your equation later on. Okay, and then you have a length of L. You are having the area of this pusher or plunger. You are given 500 mm square with a velocity of v sub p, and then you need to achieve a steady flow rate at the outlet here, which is 300 cm cube per minute, which is a volume flow rate. Okay, which is mentioned by Raj just now. Okay, so section 2, and then you need to consider there's a leakage, which is leakage is 0.1 times of the volume flow rate out of needle. So this is the equation that we're looking for in your answer, whether you understand this statement or not. Okay, this statement, actually we are expecting you to develop equation from the above statement here in the question. So we are looking for Q leak, or you can just write Q something, but you can also write leakage equal to something, equal to 0.1 Q2. Okay, so when you label something or you write equation, make sure you write in a common language where everyone see it, they understand what you're writing. So control volume, just now you label your inlet and outlet. Normally we just label as number. 1 usually is your inlet, 2 usually is your outlet. Okay, so this is a simple case where there's some case that we have a more outlet, then you have to label more lah. Okay, so in this case you only have section 1 and section 2, and then we start solving the question. Okay, stop me if you're not to understand anything happen on the screen here, or anything seems weird to you. Okay, so we start solving. So I pull the diagram to the right hand side of your screen. Then we start solving with equation. So since our control volume is moving, so look for moving control volume equation, which is this one, the Reynolds transport theorem or the conservation of mass equation. You combine with the continuity equation together. So dm over ds, or system mass flow rate, will equal to what happened in the control volume plus what happened in the control surfaces. And be careful that because our control volume is moving, so you are using relative velocity W and not the velocity as we learned early. Be careful. So for the string, for the this string example, you're having a deforming and moving control volume. So you're having a more complex scenario compared to the earliest example. Okay. So if you put tutorial questions side by side, you're able to see which equation to use. Okay. So be careful on all this information, and why it is important to equal 0, because it is an assumption that the continuity happen inside the system. There's no loss of mass inside the system. Okay. Yeah. So remember, so basically this equation will give you 2 marks if you write this equation. So first equation, first mark is here to here. I'll give you 1 mark. If you write this one and this one equals 0, you get another mark. So you get 2 marks by writing 2 equations. One equation is conservation of mass equation. Second is a continuity equation, as you apply the principle that you assume there's no loss of mass inside the system. Okay, the equation that you see on the screen here will help you to score 2 marks. If you're having a moving and deforming control volume scenario, you write this one equals 0, you get 2 marks. Okay, next, we need to solve one by one because it is deforming control volume. So there's a value here. Although inside the question, there's a tricky point there. You see the steadily, this one, don't confuse with the earlier example. Okay, steady word in the deforming control volume, it means something else. Okay, don't confuse with the early assumption. Every time you see steady, then you can cancel the control volume. In this case, because your control volume is deforming, then you cannot cancel. You cannot cancel. So we need to calculate what is the what happened to our control volume. Then we continue solving the control surfaces like the previous one. But today we're going to expose you to deforming control volume by looking at the control volume dimension. So this one, you can pull the first component out. You pull this one out, right in the new line. Okay, so you know that the m dot inside the control volume, you can write in this way. And then what else? Yeah, controls. I think this one. Okay, this one is control surfaces. Okay. Now control surfaces, you have two. You have in this case you have no. You can say you have no inlet, but you have 2 outlet. Okay, you have 2 outlet here. One is the leak. One is the nozzle outlet here. So you have 2 outlet. Okay, so there's no inlet because the water is already there, and there's no input for the volume. for the liquid. You have the leak and the output from the needle, and both are positive. You have to know why positive. Huh? You have to know why positive. Huh? All the outlet is positive. Huh? So let's say I analyze the leak. So the leak area, okay, the leak V is moving to the left. All right, the leak is towards left. And the next one, you look at the area. Area always pointing out to the opening. So the dot products for the leak is positive. And for this side, you draw the surfaces, and the volume, the velocity of the liquid is going to the right hand side. The velocity at the point number 2 here, section 2 here, velocity is going to the right hand side. Followed by area. Area always open to the opening, to the space that you have. So opening always, surface area always pointing to the opening. So 2 arrow, same, give you a positive dot products. Okay, that's why both for control surfaces here, you have positive m dot 2 plus m dot leak equal 0. So so the previous one, you score 2 marks. Then after that, you expand the equation, you will score you another marks for simplify the equation based on the diagram that you have. Okay, look at the screen. If you have anything that you want to ask me now. Anything that you don't understand. Why you have this one, why you have this one, why you have this one. If you don't understand, ask me now. Yeah. Okay, seems all of you no question. We move forward. So I already explained why positive sign there just now. So we continue solving the equation that we have just now. Your integration of your control volume plus m dot 2 plus m dot leak. So remember, this is the control surface dimension. Okay. Then we, on one side, we calculate what is this. Okay, what is the integration of your control volume? You write integration of your control volume rho v dv. So actually you have two control volume changing here. One is because of the pusher or plunger. This is because of plunger. Okay, so rho, you continue for the first one. Section 1 is rho. You continue using the rho. And how you calculate the volume moved by the plunger here at section 1. How you find the volume? Okay, section 1, you take the area of the plunger or pusher times the distance that it push. This is the area of the pusher plus the length that it travel inside the body here. So A times L, you get the volume. Okay, so this one I explained already, section 1. Then you look at the output here, at the needle section here. So you have a rho times the volume of the needle. Okay, volume of the needle. Again, if you see V with the center line at the center, it means volume. Huh? If I only write like this, it means velocity. This one is velocity. Okay, this is volume. Okay, then we know that A1, your section 1 here, A1 is AP, or the plunger is given. So plunger, the area is 500 mm square. So you can substitute it accordingly. So how do you how do you further calculate it? This is, okay, this one is only this part, right? So you need to combine the delta t for the equation. Okay, the complete equation is delta t, delta over t times the integration of rho dv. So you write the equation incomplete. You substitute what you find just now by differentiating the delta t. So both, you need this one, delta t, this one also delta t. Okay, you transform into the equation that you see on the screen on the right hand side here. Okay, so you have a del over del t integration of your control volume. You have rho a and the small changes of length divided by del t. Why do we put that? Why do we differentiate the L? Because rho is a constant value, area is a constant value. We cannot change our area here unless the question mentions something about the rho and the area. Then you need to put del in front. In this case, we know that the one thing that confirm changing is the length. As you push, the length is changing, so you have a del L over del T. Then this one also the same. So the volume of the needle, the fluid inside the needle is changing. So you put the del V here, and pull out the density just beside. So for the second term here, you write rho del V volume of the fluid that come out from the needle divided by T. Okay, so here you have the new equation that you derive from the diagram. Okay, stop me if you're not able to understand what is happening on your screen. Okay, no question, we proceed. So the next thing we can cancel. We can draw an arrow and cancel. Why we can cancel del V over del T? Why we can cancel? Okay, why? Okay, I'm going to ask question. Why we can cancel the second one? Why this one we can cancel becomes 0? Okay, I'm asking about this equation. So I give you some hints. I go back to the question. Okay, why the del V needle divided by del T times the rho, we can cancel equal 0. Okay, I show you the screen here. I'm going to ask question. Okay, who else I haven't asked today? Okay. Dinesh, look at the screen. Why we can say that del over volume, del volume over del T for the needle, we can write equal 0, or we can cancel y. Why we can cancel this term equals 0. Any keyword that you can see from the question?
The syringe injected steadily.
Okay, correct. Good answer. Okay. The keyword is injected steadily, meaning what is coming out from here cannot change with time.
Yes.
So del V over del T at this section is same throughout the time. So differentiation, del over del T is a differentiation of time. So if you have a steady flow, then you can cancel, become 0. Okay, so this is the keyword. Huh? All right, now we continue solving. So we already explained this one. The blue arrow we did explain already. So the equation will leave us del over del T integration of CV, which is this part. Arrive at rho A1 del small changes of length divided by small changes of T is a changes of your string, the string, or your push, how many length that you need to go. Basically, if you look at this, when you arrive at this equation, you know that this is what the question asking you. Okay, the question asks you what speed would the plunger should be advanced. So this is the area that you need to focus on when you solve. Okay, this is the component in the question in your answer that is important to help you to solve. Okay. Another note is that the volume, the velocity of your plunger, is actually negative rho L over del T. Okay. The velocity of the plunge here will give you negative del L over del T. Why? What do you think? Why do you think it is negative and not positive? Why? You look at the diagram on your screen. Look at this section. Look at the L. Look at this section. Why, when you move your P to the right, we can write negative del L over del T rather than positive? And what happened if you assume this one positive? What happened? Okay, give some time. Look at your screen and try to explain why the velocity of the plunger, or VP, V sub P, we can write as negative del L over del T and not positive. And why? Okay. Now again, for this module, there will be a section that will always ask you to explain the behavior of the numbers, or when you calculate something, you get a negative or positive, you need to know how to explain. Okay. Okay, Shirley, this question is for you. You try to explain why there's a negative del L over del T. What do you think?
The reason is simple because like if you move to the right, then the length will be like shorter. That's why it will be negative. If you move to the left, the length will be longer, so it will be positive.
Okay, correct. So so if the question asks you, all right, now try to understand. I can change the question. In this question, this tutorial question, the fluid is, we are pumping fluid into the body. Now, what happened in the test or coming exam? I changed this question to drawing. You know, nurse, when they draw medical checkup, they will draw your blood, right? So when I change the question to become a draw blood scenario, then your del L over del T will become positive. Take note, I start giving some hints, and you start preparing for your test or final exam already. Okay, so in this example, because you are squeezing the fluid into the control volume, into the body of the subject, so in this case, your VP is negative del over del T, like what Shirley explained just now. Because you're pushing the plunger and the L that I highlight on your screen, the L section is decreasing because you're pushing pushing the liquid to the right, okay, and out to the section 2. Remember, I try to think what happened if the question I change it to drawing blood. I draw blood, what happened to the equation that you should use? Okay, try to think and try to make it as your homework, okay, as your own revision. Try to think how your lecture will change this question and how do you solve it. Okay, in this tutorial, the liquid is pushing out from the needle. You need to think how you solve this question if your lecturer give you a question on a scenario of drawing blood. Yeah, have some time to think about it. Okay, have some time to think about it. Okay. We continue solving the question. So you can write that the first section of the equation CV, you have negative rho A 1 VP. Okay, just now Shirley already explained why this one is negative and not positive. It is because when you move this negative to right hand side, your VP will become negative. So you put back this equation. Okay, so this one, rho A1 VP will become negative. Okay, so that's why you get negative there. Then the rest is the same, m dot 2 plus m dot lick, and you continue solving. So how do you find m2 with this section 2? How do you find volume mass flow rate at section 2? You just simply take rho AV, m dot equal to rho AV sub naught 2 because it's happened at section 2. And you know that the combination of velocity times area, you'll get Q, which is the first question I asked today, and Raj is answering it. Okay. So why we need to convert to Q? Because the question already gives us what is Q. So we need to smartly know how to substitute value into our equation. Okay. Because the area at section 2 is not given. So if you don't look for alternative answer, then you will stuck here. Okay. So you need to be smart enough to change the AV to Q. Okay. Just a hint for this module. You always repeating m dot is what? M dot equal to rho AV. Or you can write a rho Q. You will see it repeat many times until the last chapter of this module. Okay. Right, so we continue. M dot lick also same. M dot lick equal to rho Q lick because you are given the okay, this one you develop from the question just now. Q lick equal to 0.1 Q2 because just now the M2 is Q, right? M2 you're using Q2, so you have the relationship between the Q lick and the Q2. So you just substitute the same parameter inside there. So your M lick in your answer there, you can substitute 0.1 Q2 for M dot lick. Okay, so you have negative rho AV for plunger plus rho Q for section 2 and also the lick rho 0.1 Q2 that you derive from the question. Okay, so this is the area. If you don't know how to develop equation from the question statement, then you are stuck at the M lick, or maybe you totally forget what is M lick in your answer, then you get the wrong output. So we continue with the question. You have Q2 and you have a row inside there. And you know that when you have a chemical, you can apply incompressible assumption as long as it is logic to use. For example, water. If you see water, then the row will be the same because we assume it's incompressible. So if you're having a chemical and every time you pump a chemical into a subject, the row will always assume as incompressible. Okay. So the rest is just mathematics. Okay. So you just simplify. So this one plus this one, you get 1.1. And row just now, you can take out because incompressible. And then you rearrange, you'll get this term. Okay, rearrange this one, you get velocity of your plunger will equal to 1.1 Q2 divided by A1. Okay, Q2 is given, which is 300 cm over minute. A is given, however, be careful on the unit. A is in mm square, Q is in cm cube. You need to change mm to cm, okay, so that you can cancel, it become in cm cube. Okay, of course, in the test or exam, you will be instructed, you will be given a clearer instruction where you will see you need to put your answer in the certain unit. Okay, this is a tutorial question, so it will be more open-ended kind of question. So you substitute all the value just for your revision. The answer for your check will be 660 mm per minute. So the answer that you see on the screen here, it means that we convert cm cube to mm. Okay, yeah. So basically, it's just an application of just a substitution of all the numbers. Just be careful on the unit, and then you look at the instruction in the question, whether the question asks you to solve in what kind of unit. Then you convert accordingly. Okay, so this is how we apply for the deforming moving control volume. This is a Springer. Okay, in this case, it's a Springer example. Okay, we have a short break here. Let me stop the recording.